This screencast is about including the square of a basic variable in a model. Such squared terms are called quadratic terms, and models with quadratic terms are called quadratic models. The simplest example of a quadratic model involves one base variable. As indicated in this expression, where the deterministic part of the model is equal to the intercept beta naught plus beta 1 x1 plus beta 2 x2, where x2 is just the square of x1. We can think about this expression as beta naught plus beta 1 x1 plus beta 2 x1 squared, which would graph as a parabola. In this example, the question is, how many units of an additive should be used per gallon to maximize a standard car's miles per gallon? Here's the data. The independent variable, call it X, is the units of additive per gallon of gasoline. The dependent variable, Y, is miles per gallon of the standard car. A scatter plot of the units of additive per gallon versus the miles per gallon has a parabolic shape. We prepare the data to fit a quadratic model by including a units of additive per gallon squared column. When the quadratic model is fit, we obtain an adjusted R squared of 98%, a residual standard deviation of 0.3 of a mile per gallon, a model that tests as overall useful, with both the units of additive per gallon and units of additive squared per gallon terms also testing as useful. When the coefficients in the coefficient table are used, we can write the estimated regression equation as y hat equals the intercept plus the slope of units plus, well, actually minus the slope of units squared. We have moved to the next page. The residual analysis indicates the model assumptions are satisfied. Note that a scatter plot of the residuals versus the quadratic term, units squared, is not included. Such a plot would show the same vertical pattern of residuals as the scatter plot of the residuals versus the linear term, units. Thus, only a scatter plot of the residuals versus the linear term is required for a residual analysis when a model also contains the square of that linear term. Now that we know we have a good quadratic model, we can proceed to determine the number of units per gallon of the additive to maximize the miles per gallon. Based on the scatter plot of the data, we would expect the miles per gallon maximizing number of units of the additive to be between 2 and 3. To get a more precise value of the miles per gallon maximizing number of units of additive, we differentiate the estimated regression equation for miles per gallon with respect to units of additive x. This derivative gives the slope of the tangent line to the graph of miles per gallon. The value of x, where the tangent is flat, indicates the number of units of additive that maximize the miles per gallon. When we include 2.442 units of additive per gallon of gasoline, we obtain the standard car maximizing miles per gallon of 31.79 miles per gallon. This concludes our first example of a quadratic model. For the next example, we return to the use of radio advertising expense and newspaper advertising expense to predict monthly sales. A primary concern in using the previous models was that of the curvature we observed in the residuals versus radio and the residuals versus newspaper plots. In an attempt to improve these residual plots, we fit the double quadratic model. Sales equals beta 0 plus beta 1 times radio advertising expense plus beta 2 times radio advertising expense squared plus beta 3 times newspaper advertising expense plus beta 4 times newspaper advertising expense squared. Next, the data has been prepared in Excel to fit the double quadratic model. We have inserted a radio squared column and a newspaper squared column. If the regression is done based on the data arranged in this way, we'll be using the dependent variable sales and then the independent variables that appear in columns C through F. The radio advertising expense variable will be the first independent variable. The second will be radio squared. The third independent variable will be newspaper. And the fourth that will appear on the output is the newspaper squared variable. We've moved to the next page. The double quadratic model has an adjusted R squared of 90.7%, an improvement over the 87.2% of the interaction model from last time. The residual standard deviation of $105,185 is also an improvement over that of the interaction model from last time. The double quadratic model tests as useful. The radio squared variable tests as a useful variable, and in this type situation, most model builders would keep both the radio squared and radio variables in the model. The newspaper squared variable also tests as a useful model. And as with the radio and radio squared, most model builders would keep both the newspaper and newspaper squared variables in the model. Keeping the second variable, radio or newspaper, is costless. There's no additional data collection required. The residual analysis appears on the next page and the page following that. Note that the residual analysis is excellent. The problem we had before of curvature in the residuals versus the radio advertising expense no longer exists. And the same comment applies for the curvature that we had before in the residuals versus the newspaper advertising expense. The normal probability plot is good. Overall, this model is an excellent model. Using the Excel regression output, we can write the estimated regression equation. Using the double quadratic model to estimate monthly sales at a given level of radio advertising expense and newspaper advertising expense is straightforward. Simply plug in the radio advertising expense, the radio advertising expense squared, the newspaper advertising expense, and the newspaper advertising expense squared into the estimated regression equation. For a current amount of radio and newspaper advertising, to decide where best to spend an additional $1,000 worth of advertising budget is a calculus problem. That problem would be done as we did last time when we worked with the interaction model. This completes our discussion of the double quadratic model. Next, we append the radio newspaper interaction term to the double quadratic model. We prepare the data and fit it. The adjusted R squared is 91.8%, an improvement over the double quadratic model. The standard error is now below $100,000 at $98,674, again an improvement over the double quadratic model. The model is useful, and both quadratic parts seem reasonable to include, as does the interaction term. You have not been given a specific significance level that you need to adhere to. We've moved to the next page where we've included an overall evaluation of the double quadratic model with interaction. You should read this page. Our general conclusion is it's a good model, but we should avoid attempting to add additional variables. We are pushing up against the principle of parsimony, which says select the simplest model that gets the job done. This completes this screencast on quadratic models.